So here we have a triangle that doesn't have a right angle. Because it doesn't have a right angle, there's no hypotenuse. And that means we can't use our good friend SOHCAHTOA to find any of the missing sides or angles. Fortunately, there is another very clever trigonometry trick that we can use instead. It's called the sine rule. Starting with any random triangle, so not necessarily an isosceles, doesn't have a right angle, just any old triangle. We start by just giving the sides of some names. So I'm going to take that one and call it side A. I'll call this one side B. And finally I'm going to call this one side C. Now it doesn't matter which side I label with which letter, but the following does matter. This is really important. If I now label the angle opposite side A, we have to call that one capital A. And then I label the angle opposite side B, and I call that one capital B. And now, if I label the angle opposite side C, I have to call that one capital C. Now the sine rule tells us the following. If I take the sine of angle A, just put that in a calculator, and divide it by the length of side A, the side that's opposite it, I will get a number that is exactly the same as the number I'll get if I take the sine of angle B instead and divide that by the length of side B. Even stranger, I get exactly the same number again if I take the sine of angle C and divide it by the length of sine C. So there you have it. That is the sine rule. So now I just want to demonstrate that this is a real thing. This really does work. I'm not making it up. Here I've got three triangles that have all been labelled already. You can see all their sides and their angles. Let's start with just this triangle here. Right. So if I label a couple of the sides, just so we know what we're talking about, we'll call that one has to be side A, it's opposite angle A. And then we'll look at side C as well, that one there. Now what we're going to do is we're going to look at the sine of angle A, we'll divide it by the length of side A, and that should be equal to, should get the same number if we do the same thing with angle C and divide it by length C. Now these numbers on the triangle have been rounded a little bit, so when we do this, the number we get should be very, very close, but it might be just a little bit different. Okay, so angle A is 68, so looking at sine 68, and side A was 4 centimeters, so we'll divide that by the number 4. We'll change colours now. I'll highlight angle C, that's 44 degrees. And we're going to divide that by side C, which is 3 centimeters. So starting with sine A over A, if I bring up my calculator, 68 sine, then divide that by 4, I get 0.232 to 3 decimal places. And now I'm going to do the same thing now for angle C and side C. Sine 44, divide that by 3, and I get 0.232. So those two numbers were exactly the same. I'll do the same thing again now, just another quick demonstration using one of the other triangles. So let's use this triangle here. And we'll look at angle C and side C. And this time we'll look at angle B and side B as well. So first of all, if I write down the sine rule, I take the sine of angle B divided by length B, I should get the same thing. I should get the same number if I do that for angle C and side C. So angle B is 53.1 degrees and length B is 4 centimeters. So dividing them should give me the same thing if I take the sine of 36.9 and divide it by 3 centimeters. So let's see what happens. 53.1 sine, divide that by 4, 0.1999. That's 4 decimal places. Now let's do the same thing with angle C. 36.9 divided by 3. Let's try that again. 36.9, take the sine of that angle, now divided by 3. 0.2001. So those two numbers are very close to each other, almost exactly the same. Any error that's crept in is because that number there and that number there have been rounded. So that's a little bit about what the sine rule is. Now how do we actually use it? Well, like with SOHCAHTOA, the first thing you need to do is make sure that your diagram is fully labelled. So I'm going to just add this in here so I know that's side C. I'm just going to add this in here as well so I remember that's side B. The next thing that we need to do is write down the 3 angles and the 3 sides. Now angle A we don't know yet. Angle B we don't know either, but angle C we know is 42 degrees. Side A we don't know. Side B is 6 centimeters and side C is 5 centimeters. Now what we're looking for here is a matching pair, like this one here. We need one length and one angle that belong to a pair, and we know them both. We need that in order to be able to use the sine rule. If we don't have that, when we actually write down the angles and the sides, we can't use the sine rule. In this question, we've just been asked to find all of the missing sides and the missing angles. So the next thing that we need to be able to use the sine rule is to look at another pair, like this one here, where we know at least one of the 2 pieces of information, either the side or the angle. So for the B's, we do know the length of the side, we don't know the angle. We can use the sine rule now to find that missing angle. So now we write out the sine rule. Sine b over b equals sine c over c. From this point on, it's just substitution and rearranging exactly the same way as we did for trigonometry when we did SOHCAHTOA. So first of all, sine b, we still don't know what angle b is, that stays. But side b, we can put that in, it's 6 centimeters. Angle c, we know is 42. And side c is 5 centimeters. So now we can rearrange this by bringing this 6, which is a divide by 6, up to the top on the other side of the equation. So it becomes a times by 6. So sine b is equal to 6 times by sine 42, all divided by 5. If we put that into a calculator now, that will tell us sine b. 42 sine times by 6 divided by 5. Okay. So sine b is 0.803. Which means b will be the inverse sine of 0.803. So if I now take the inverse sine, there we go. B is 53.4 degrees. And straight away, now that I've got that, I'm going to write it into my diagram. 53.4, and I'm going to write it up here as well. So we're done with the B's. We found angle B. Now let's look at the A's. Now here we've got a problem because I said we needed to know at least the length or the angle in order to use the sine rule to find the other one. But actually, if we have both angles of the triangle, here and here, we can find the third one very easily. Angle A is just 180 degrees. Take away 53.4 degrees. Take away 42 degrees. 180. Take away 53.4. Take away 42. 84.6 degrees. So that was even easier. And now that we have that, we can find angle A as well. So it doesn't really matter which pair I use in order to try to find angle A, but I might have made a mistake finding angle B. So because I know these two numbers must be correct because they were given to me in the question, I'm going to use sine A over A equals sine C over C. I'm going to substitute in my numbers. We don't know what A is yet. Sine 42 over 5. Now, rearranging this can look a little bit tricky, but it's really not too bad. The first thing I need to do is get the a off the bottom of this fraction. So I'll take it to the other side, and it becomes a times. And I'll get this 5 off the bottom, taking it to the other side over here. And finally, I'll get this a on its own by taking the sine 42 to the other side. .6 divided by sine 42. Now that I have that, I can work out the length of side A just by typing 84.6 sine times by 5 and dividing that by sine 42, which gives me side A as 7.44 centimeters. And so there you go. Using the sine rule, we've been able to find all the other missing angles and lengths in this triangle.